So section 4.2, we're going to continue to go over probabilities. And we'll start with kind of a little bit of a reminder or a blast from the past, the last section. It says, when randomly selecting an adult, let B represent the event of randomly selecting someone with type B blood. What is this probability, or what is this statement saying? Probability of B or B bar equals 1. What do you suppose is going on with that? Tahara?
C, like is a chance to get either one. I don't know.
Yeah, so what this is saying is that if you flip a coin, you're going to get heads or tails, probability 1. Or if you choose somebody at random, either they're going to have type B blood or they're not going to have type B blood. A or not A, B or not B. That will happen with probability 1. So you're exactly right. Now, in this case, only one of these can happen, right? Either heads or tails. There's no overlap. That makes these things mutually exclusive events. So that's going to make calculating these probabilities a little bit easier, because if the events don't overlap, then you can calculate the probability of A or B, this or this, by adding up the probabilities. We're going to use that down here, but we're going to kind of extend this as well. So let's look at this example down here, example B. Example B comes with a nice little table here. And there was, I think the restaurants A, B, C, and D are the same ones as down below: McDonald's, Burger King, Wendy's, and Taco Bell. We're just going to go with A, B, C, and D. I am going to introduce some of my own notation here, though, just to make things convenient. Because I've already used letters like A and C for accurate or correct, let's just call this, we got the right answer, or the right order, or the wrong. So I can use R or W to denote those kind of events. Now, I have given you a little bit of help on this, and that is we've turned this into a t-table here and here. So you've got 1,134 users that were sampled for this table. Okay, that's fine. Let's see what we can do with the first question. What's the probability of getting an order from restaurant A or restaurant B? So let's write that. Probability-wise, that's probability of A or B. One or the other. And kind of a first thought on something like this might be say, well, let's just add them up. The probability of A plus the probability of B. And that, in this case, is actually going to work. It's going to work fine. So let's figure out the probability of randomly picking somebody from these 1,134 people that went to restaurant A. How many went to restaurant A from those 1,134 people?
362.
362, good. So 362 out of 1,134. 362, 1,134. How many people went to B?
325.
325. So 325. And that number would be here. So 325 over 1,134. Overall, it gives me a total of 687 over 1,134. So, all right, a pretty good majority of people that went to A or B. Fine. Let's change things up a little bit and see what happens when we change this to the probability of getting somebody from restaurant A or getting an accurate order. So that's a little bit different. Probability of A, or that they got the right order. Remember, that's up here. So, or R. And if I approach this the same way, something interesting is going to happen. Now, don't copy this down just yet. Just hang on for a second. And let's see what happens if I take kind of the same naive approach that I did with the above one. I could say probability of A plus probability of R. Probability of A, we already know, that was 362 out of 1134. Probability of R. Well, how many people got an accurate order? How many? 989 out of 1,034. So that gives me a total of 1351 over 1,034. Okay. Can anyone suggest a reason why I said don't take any notes just now? Ah, well done. This is bigger than 1. Remember back from our last section, probabilities are between 0 and 1. You can't have a probability outside that range. So if you get something like this, that should be screaming out at you, there's something wrong. Typically speaking, if I was grading something like this, I'd just mark it wrong. I don't know as though I'd look around for partial credit. That should scream out at you that there's something wrong. So let's see if we can't figure out what went wrong here. And I think we can take a look at it graphically. So if we look at the first part, probability that we order from restaurant A, that's going to be here. So we'll add up those. And then we'll also throw in probability that your order was accurate or got it right. And if you notice, something happened right here. You're counting these people twice, right? You counted them once going down, you counted them once going across, so there's a double counting. So we gotta take care of that. And the way we take care of that is we subtract what that is. And that's the intersection of A and R. So probability of A or R is gonna look like this. It's the probability of A plus the probability of R minus the probability of their intersection. Probability of A and R. Where do they overlap? Okay. So we're getting rid of that double counting is what we're doing. Probability of A, we already know. That's our 362 over 1134. Probability of R, we went over that as well. 989 over 1134. But how many are in A and R? What does A and R actually even mean relative to this context, right? What does A and R mean, in words or numbers, whatever works for you?
The probability of getting A versus an accurate order.
All right, it's the probability of getting an accurate order from A, right? So you're looking for where both of those happen at the same time. James, how many places, or what's that probability of getting an accurate order from A and R? How many people have got an accurate order from A?
362. Okay.
That's the number of people that had an order from A, but an accurate order would be, yeah, there you go, 330. Okay. Let's add these together, and let's see. I think that's going to be 1,021. Someone double check my math on that one. 1,021 over 1134. At least that makes sense now. At least it's a legitimate probability, as opposed to the last one we knew had to be wrong. So that's our final answer here, like that. So why didn't I have to worry about this kind of thing with the first one? Well, the reason goes back to the kind of events that these things are. And when A and B have no overlap, there's a couple things we say about those, or a couple different terms we use. So if A and B are mutually exclusive, so A and B are mutually exclusive, then when one happens, the other can't happen. Now, I like the term mutually exclusive because it kind of reminds you about what these actually are. It means one excludes the other. If one happens, the other one can't happen. So, now there's another word for this that the book uses more often than not. I like mutually exclusive, but you can also use disjoint. Also said to be disjoint. And I'll probably use both of these, but like I said, I like mutually exclusive because if you think carefully about what this is saying, then it's telling you that one excludes the other, that they can't both happen. So let's talk about what's called the general addition rule for probabilities. So probability of A or B is going to be the probability of A plus probability of B minus probability of their intersection. That's in general. If A and B are disjoint, what's this probability? If A and B are mutually exclusive, what's the probability of A and B? 0. Yeah, they can't happen if they're mutually exclusive. So you have what's called the special addition rule. Probability of A or B is a probability of A plus probability of B. That you can use if and only if A and B are disjoint. So that's the special addition rule. So that's really what we were using in the first case, because in the first case, A and B were mutually exclusive. You can't order from restaurant A and order from restaurant B at the same time. So those are mutually exclusive. That's why we're able to get away with this. Here, you had to account for that double counting. All right, so mutually exclusive is one term that we're introducing you to now. I'm going to introduce you to another term. Before I introduce independence, are we okay with mutually exclusive? So for instance, mutually exclusive could be flipping a tails on and flipping a head at the same time. I can only flip one of them. I can't flip both. So you're either heads or tails. But we're going to move towards something called independence. So we're going to work with the probability of A and B. And that eventually leads to a discussion of independence. So a similar table to the one above. I actually took the time to put in some names here in terms of McDonald's and whatnot. Same kind of thing. But we're trying to illustrate a different idea here, which is independence. Okay. In this table, we're going to let B1 and B2 represent the idea that you're randomly going to select somebody who went to Burger King, on the first draw out of the 2 draws on this table, and then you're going to draw again, and on the second draw, B2 represents the probability that you drew somebody out on the second draw. So what I want here is a probability of B1 and B2. Now notice this is different than what we had just a moment ago. A moment ago, I said A or B, or A or, or getting an accurate order. Now, both of these have to be satisfied. We're going to do this in 2 different ways. We're going to do with replacement and without replacement. With replacement seems kind of silly sometimes, but it is going to get us to what we need. If you're looking at the probability of B1 and B2, well, for both of these things to happen, the first one's going to happen. What's the probability that the first one happens? What's the probability that you randomly select somebody that ate at Burger King here?
362 out of 1,118. Oh,
Right.
318.
There you go. Thanks, Omar. 318 over 1,118. Now, for strange reasons that go beyond what I could comprehend, you're going to look at that person and say, okay, and put them back in the table, shuffle up the results, and draw again. So what's the probability now that you've picked out that person, put them back in and shuffled, that you get another person that ate at Burger King? Don't think too hard. 318 over 1,118. That's it. That's all I'm looking for. You could write that a little bit more compactly as 318 over 1,118 squared, which I would like. I'm not sure you get an extra credit point, but you might get at least a smiley face. That's cool. That's worth it. How about without replacement? That's going to change things, at least a little bit, but not on the first guess. On the first draw, you're still going to have a 318 chance out of 1,118 people in this table. But suppose you did get lucky on that first guess, and you pulled out somebody that ate at Burger King. This time, you're not replacing them. Rianne, what's going to be that probability of drawing out another person who ate at Burger King? 317?
Over 1,117.
Good. The numerator and denominator both change. And that's kind of interesting, because what it's saying is that what happened on this first event affected what happens on the second event. These are related somehow. They're dependent. So that's something I want to discuss a little bit more. On the back side of this, you've got a definition of dependence. Events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other one. So here, sampling without replacement, that's going to lead you to dependent events. What happened on the first result changed the probability of the second result. How about over here, sampling with replacement? Did what happened on the first result change the probability of the second result? Nothing? No. So these are independent. Independent. So sampling with replacement yields independent events. Sampling without replacement yields dependent events. Suppose I'm flipping a coin. I got heads on the first flip. Does that affect the probability of my heads on the second flip? So those kind of events would be independent. And this is really at the heart of something called the gambler's ruin. A lot of times people think that, oh, I've been at this slot machine for an hour, hasn't paid off, it's due. No, it's not. It's just luck. It's just like if I flip this quarter and I got 10 heads in a row, you might say, oh, it's due for a tails. No, it's not. The quarter doesn't have some chip in it going, well, you know, I've come up heads 10 times in a row. I better come up tails to be even. No, they're independent. What happened in the past doesn't change what happens in the future. So, you know, if you're at the table for a while and you're continuing to have bad luck, your chances don't necessarily change moving forward. Your chances are still the same. They're independent events. Okay. All right, let's do an example like what you're going to see in your homework. I gave you this table, but this time I didn't fill it in because you're going to have to fill in a table like this for yourself. So let's see if we can't do that. Talks about the results from a one-panel THC test and for marijuana use, which maybe they should update that because it's increasingly legal all over the place. But they don't tell you exactly how to put in the numbers. So you're gonna have to think through this kind of carefully. 140 subjects tested positive. 143 subjects tested positive. Where am I gonna put that number? The total for positive. Perfect. So that number goes right down here. So 143. There are 24 false positives. All right, so that's another number I want to keep track of. 24 false positives. Where should I put the false positives?
Doesn't give you a positive test?
Yeah, right here. If they're a false positive, they got a positive even though they didn't use. So 24. Now they don't give me the top number there, do they? But what would that top number be? Dylan? 119. Good, you subtract. So 119. We can do the same thing with the 157 negative results. See if you can't finish filling out this table. Caitlin, where should I put the 157? I'm sorry, I'm still, wait, Katerina.
Yeah.
There we go.
In the total.
Yeah. 157, that goes down here. And then it says there are 3 false negative results. Dylan, over here to my right. Where am I going to put that 3 false negatives? To my right, yes.
It doesn't use.
Doesn't use.
They're negative.
Yeah, wouldn't that be a correct result if they don't use and they got a negative result?
Yeah, since but it uses negative.
So that 3 would have to go up here.
And 154.
Yes, and then 154. So across the top, that gives me 122. Down here, I get 176. 178, how about that? 178. And yeah, that looks like it works out pretty good. So some of these you might need to fill in your own table. All right, that's a little extra work that you get to do at no additional cost. Let's see if we can answer some more questions here. Let N1 and N2 represent the event of randomly selecting somebody who tested negative on the first and second draws respectively. So kind of like the last example, we're going to do one with replacement and without replacement. See if you can't bang these out. If you're watching this video later, then maybe fast forward until I get rid of my pause button. to come up with probability of N1 and N2 in those two circumstances. And I'll walk around and help out.
So far, so good.
There you go. Good catch.
Yeah.
Good. That's the first one. Move that one to the back. I'll do the second one. Same thing. Yeah. So I would want that one. All right. Okay, so let's take a look at these. Let's see, rain. What'd you get for the first one?
157 over 300.
157 over 300. And the second one?
Same thing.
157 over 300. And walking around, a lot of you did this, which is 157 over 300 squared, which I like to see. Cool. Maddie, what's going to change when I sample without replacement?
I did 157 over 300 times 156 over 329.
All right.
299, I don't know why I did.
That's all right. I just put down what you meant.
Yes.
Which I'll do on the test for you guys, okay? I'll just write you on, I'll grade you on what you meant, all right? All right.
There you go.
Yeah, and that's fine. That's all I'm looking for right here. So which one of these is independent of the other one?
A.
Yeah, A. Because the result of the second trial doesn't have anything to do with the result of the first trial. Those probabilities are the same. Here, they're close to being the same. And in fact, the author has kind of something pretty convenient here, which is called the 5% guideline. If your sample size is less than 5% of your population, you can treat them as if they're independent, even though they're not. So if we were to actually calculate both of these probabilities, they'd be ridiculously close to each other. So let's try that and clear this out and this out. So I can do 157 divided by 300 and then square that result. Or I could do 157. Actually, you know what? Here's a cool trick for you guys. So you don't have to worry about parentheses so much. If you hit the alpha key, then the y equals key. The first option there lets you do fractions. So I'll do 157 divided by 300. And then times, and I'll do this again, alpha y equals, first option there, 156 divided by 299, and bam. So it actually gives me a decimal or a fraction there. If I wanted a decimal value, 157 divided by 575. Is there a big difference between these two probabilities? Pretty small. Which one do you think is more convenient to calculate? First one or the second one? First one. So 5% rule is something we're going to use when we can. And it basically says if there's less than if your sample size is less than 5% of your population, treat the results as if they're independent. So this is approximately the same thing I would get if I treated them as independent. It's not perfect, but it's close enough. I'm not sure that trick is as useful as it used to be, because now we've got so much technology that it's very easy to put this stuff in, but we'll still go with it. Last but not least, find the probability of someone using marijuana or testing positive. This is a good review of some of the stuff we just done. Probability that somebody uses marijuana. Let's see, I need to probably to use or test positive. So I'll abbreviate that positive as probability of U or P. Now, the way that we've looked at things in this class, we're going to have to use our addition rule, our general addition rule. So it's this stuff. Probability of A or B is the probability of A plus probability of B minus the probability of their intersection. So what would that look like here?
Is it 122?
Let's fill in the symbols first. Haley, what symbols can I fill in here? Probability of U.
Or
U.
just, U, and then P, and then we can minus it by U.
And
Okay.
and P. So you're looking for their probability in their intersection. So try and fill in some of those probabilities. It's the last one in particular that is going to be a little bit challenging. But think about what that is. Users and testing positive. Let's look through these. Georges, what's the probability that somebody uses in this table? There's more than 3 people that used.
Wait, uses like negative and positive? Oh,
Yeah.
122.
All right, hopefully you don't just put 122 though, right? Or how many people in the table? 300, good. Rain, how about what's the probability of testing positive?
143 over 300.
Yeah, 143. Let's make that look like a 3. 143 over 300. Omar, how many people use and tested positive?
Should be 20. No. Use and test positive?
Use and test positive. So you're looking for the intersection of 2 things here.
I thought it was 24.
Those are don't use, right?
Yeah, but it should be 1 and 2.
Yeah, 119, good. So 119 over 300. So I think that's going to give you 146, right? Over 300. And that's it. That's it for this one. So kind of a good refresh on your general rule for addition. But we're going to definitely be doing some work with this stuff. Do practice on it though. Comments or questions here? All right, let me stop this here.